All right, a good way to start a Wednesday afternoon with a little bit of synthesis. Okie doke. So let's see here. We kind of left off with this question. We solved this question here, and then we said we'd pick it up on Wednesday with these questions here. So the first one, we have two functional groups that are next to each other. And if you remember what it said in the slides that we looked at last class, it said something about if you have two functional groups, oh, I don't know where it was. It was right here. If you have two functional groups that are adjacent to each other, you might want to think of starting out with an alkene. And you can see that the answer to the question that we're looking at is kind of shown right here at the bottom. But anyhow, kind of cheated on that one a little bit. But anyhow, that would be your kind of retrosynthesis. You'd say, well, I'm going to start with an alkene if I want to have two functional groups next to each other. And of course, we have an alkene. And so maybe a better retrosynthesis here would be if I had this epoxide, right? If I had this epoxide, then, oops, I guess there's only one methyl group on this side. Yeah, if I had this epoxide and I treated that with cyanide, so if I treat this with cyanide, Cn minus, right, that's a nucleophilic ring opening, so it's going to attack the least hindered side, and that's going to end up giving me the desired product. And so how would we go about making that epoxide? Well, there's nothing new there. So let me just kind of write the reaction arrows here. To make the epoxide, we treat it with MCPBA, and that will give us the epoxide, the one that I have drawn in blue, but I'll just draw it over here. So here's our epoxide or our oxirane. They both mean the same thing. In the next step, we're going to treat that with sodium cyanide because we need cyanide as a nucleophile. So sodium cyanide as a nucleophile. And of course, that's going to do an SN2, and it's going to attack the least hindered carbon. And that is going to give us this compound. So something very close to what the final product is. But now we have an oxide. And then we can treat that with aqueous acid or with water. Water is a strong enough base. We'll just treat it with H2O. And that's going to protonate the oxide, and that will give you the desired product. Okay, the next one's not the greatest question for this chapter because I could have asked this in previous chapters, although it does. We do have to go through an epoxide if we want to make a transdiol, right? If we want to add two hydroxyl groups in an anti-fashion to make a transdiol, then to do that, we want to proceed through an alkene. So the question becomes, how do I make this alkene? Because if I treat this with MCPBA, followed by aqueous acid, it's going to give me the desired product. So could anybody tell me what the first step has to be? If I'm starting out with cyclopentane, what does the first step absolutely have to be? There's no questions. There's only one possibility. Yeah, thanks, Audrey. It's bromine and light, so Br2 and HU, absolutely. Right, and then we're going to hit it with a hindered base. Why? We could hit it with sodium methoxide. That will give us some elimination, but it'll also give us some SN2. And so if you hit it with a hindered base, like 2-butoxide or DBU or DBN, then that's going to give you almost exclusively the elimination. I'll try DBU. We don't use that a whole lot. Diazobicycloundecane. So that gives us the alkene. Then we're going to treat that with our peroxy acid. If you put MCPBA, that works. If you wrote peroxy acid like this, that's totally fine as well. And then that's going to give us our epoxide. And then to crack that open and to make the transdiol, what do we have to hit that with? Anybody? It's my last step in this case, to open up the epoxide. Can anybody tell me? Can you guys hear me? If I want to take an epoxide and convert it into a transdiol, this goes back to chapter 8 of Organic 1. Can everybody hear me? Can anybody hear me? Okay, good. Thanks, Nicole. Yeah, so how would I crack open an epoxide to make a transdiol? Anybody? Yes, it's going to be with aqueous acid, right? we have to treat it with aqueous acid, and that's going to open up the ring, right? And that's a mechanism you have to be able to draw. All right, so there we go. So again, that's a question I could have asked on a chapter 8 quiz, or yeah, chapter 8 quiz. And the first one is also pretty straightforward too. That just uses old chemistry, but it does include or incorporate an epoxide. So that's why it's pertinent to this chapter. Let's move on to these ones a little more complex here. You can see that in the first one, we're starting it with 6 carbons, and then we're ending up with 8 carbons. So we're adding these 2 carbons here, but we're adding the functional group to the very first carbon that's attached to the ring. And so for that, if we do our retrosynthesis, we're going to want to think about using, a Grignard reagent, but we would want to think about using an aldehyde like this, something that's 2 carbons and has a carbonyl in it, right? Because that will do a nucleophilic attack on that, and that means all we have to do is protonate it with aqueous acid, and that will give us the desired product. All right. Another way you can do this one is kind of a cheater method. Not cheater, but it's not really proper chemistry. But you can kind of draw a backwards arrow like this, and say, well, and again, these arrows don't mean anything, okay? This is not reality whatsoever. But if you look at those arrows, it would produce this aldehyde, okay? I'm going to erase those because I don't want any permanent record of those anywhere. But yeah, you would want to use this aldehyde, which is called acetaldehyde, as your electrophile. So what's your synthesis going to look like? Could anybody tell me what the first step of the synthesis will be here? When I take my cyclohexyl bromide and I want to convert that into a good nucleophile, how would I make that into a nucleophile? Yeah, exactly. I want to turn it into a Grignard reagent. Thanks, Tiana. Absolutely. So let me just move this over a smidge here. So I'm going to treat this with magnesium and diethyl ether, and that's going to give me a beautiful Grignard reagent like that. Then in the next step, I'm going to treat it with my acetaldehyde molecule. So that's going to attack the carbonyl group. And we're going to end up with this oxide that looks like this. And then all we have to do is a proton transfer. And so we're going to treat that with water or aqueous acid. I'll just put H3O plus. And these are mechanisms that you can practice drawing all the time. Can never get enough practice on mechanisms like that, and that will give you the desired product. Just like that. So we end up with this secondary alcohol. I'm going to move to a blank document to do the next two, just so I have a little more space. Just bear with me. Oh, okay, you want to be that way? Fine. All right, so let's see here. So this is question 13.24. And we are on question, this one is actually C from the textbook. So we're starting out with cyclohexyl bromide, and we want to convert it into this compound where we have our hydroxyl out here. So it's 2 carbons away from the ring. And then we have a geminal dimethyl group here. And if you remember last class, I kind of showed you my backwards way of doing it, where if you say, okay, well, I'm going to connect this bond here, and I break this bond like that. And again, this is nothing. This is not proper arrows at all. They don't mean anything. It's not resonance. It's not a mechanism. It's just a way of kind of connecting the dots backwards. And so if you were to connect those dots backwards, what would be the 3-membered ring or the epoxide that you would need? You would need this epoxide, right? You'd need 2,2-dimethyloxyrenine as your electrophile. And you would go through a Grignard sequence much the way we did in the last problem. So, like Tiana said, we're going to start out with magnesium in diethyl ether, and that's going to give us the Grignard reagent, which is a great nucleophile. And so now all we have to do is treat it with our electrophile, which is the 2,2-dimethyloxyrenine. And remember, this is a nucleophilic ring opening, so it's just going to attack the least hindered carbon. You're going to open up that ring, that 3-membered ring, which is highly strained. You end up with 2 carbons. So look, if I count carbon 1 and 2, this is carbon 1 and 2. What's attached to carbon 2? I've got 2 methyl groups, 1, 2. And then I also have an oxygen, which is going to have a negative charge on it. And now I need to protonate that in the last step. So I'm going to treat that with aqueous acid, and that's going to give me the desired alcohol. All right, so that covers C, and the next one I believe is, I wrote it down as question D, I think it is. So this is 13.24, so this is Klein, 4th edition. Okay, this is 13.24D. All right, so we're starting out with our cyclohexylbromide. It seems to be the molecule of the hour here, and we want to convert it into this ketone. So we want to make cyclohexyl isopropyl ketone is what you would call this guy here. So could anybody tell me what they did as a strategy for this one, or how this would differ from the other ones, or any ideas at all? Could anybody unmute their mic and maybe tell me a strategy for this one? I'm always open to suggestions. What would I use for an electrophile for this one? Yeah, right, Maria? We're going to have to do an oxidation as the last step. So what Maria is saying, and she's totally right, is she's saying, well, her retrosynthesis started like this. You know, I could make this alcohol using Greenyard chemistry, and that means the very last step would be an oxidation, right? So you could use PCC or Jones or Swern or Des-Martin, whatever you want, really. So then the question becomes, well, how do I get from here to here, right? So you shorten it by a step. So what kind of functional group do we need to have in our electrophile that we're going to use? We're going to make our nucleophile when we convert this into a Greenyard reagent, right? So we treat this with magnesium and ether, all right? And that gives us this compound, okay? So remember, this, what's in this box here, I guess I don't even need it. This here is a nucleophile, right? It's seeking a nucleus. So what's going to be my electrophile? Or, thanks, Tiana, exactly. The functional group that's going to be in my electrophile, which is going to have these 4 carbons in it, the ones that are in the red box, has to be this. I have to have a carbonyl, and it's got to have an isopropyl group on one side. Like that. There you go. So, perfect. That's going to be our electrophile. So our nucleophile is going to attack the electrophile like so. That's going to give us the oxide. So we'll draw the oxide like this. Put our isopropyl group. We're going to treat that with H3O plus. That's going to give us the alcohol. So here's the alcohol. And then to oxidize that, you can use whatever you want. I'll just pick PCC because it's easy, pyridinium chlorochromate. And there you have it, my friends. All right, so a little bit of synthesis problems here. Are there any questions in particular in the back of the book, in the suggested problems, synthesis problems that anybody wanted to look at in particular? If not, that's totally fine. But if there's anyone that just puzzled you, nobody sent me, it's interesting, nobody sent me any emails about synthesis and said, you know, this one's the worst or something like that. All right, let's go back in chapter 13. Now let's switch gears back to nomenclature because there was a few problems. Where were they? There's a few problems we did not do. And nomenclature of, yeah, these ones here. Okay, Wednesday. All right. So here we go. Let's see if we can solve these 2 beasts here at the bottom. These ones are not easy, right? If it was easy, anybody off the street could do it. So let's see if we can tackle the first one. Why don't we start by naming it as an oxirane? We'll start with that. So if we want to name it as an oxirane, we're going to have groups 1, 2, and 3. And well, we have an ethyl group and a propyl group. We'll go by alphabetical order, right? Because if this is 1, you know, is your 2 here or here? Well, we're going to pick 2 on the right-hand side because that would be an ethyl, right? And ethyl comes before propyl in terms of alphabetization. So 1, 2, 3. So we have a 2-ethyl, 3-propyl oxirane. So we could scribble that down right away. So let me just scribble that down here. I'll put 2-ethyl, 3-propyl oxirane, like that. And now we need to figure out the stereochemistry at carbons 2 and 3. So I'll put 2 something, 3 something, and hyphen. All right, here we go. Let's see if we can figure out the stereochemistry at carbon number 2. So carbon number 2 is this one here. Our highest priority group is going to be the oxygen. We have a hydrogen that's coming out in front. That's going to be our lowest priority group. Then we have this carbon here, which is attached to oxygen, carbon, and hydrogen. And then we have this carbon here, which is attached to carbon, hydrogen, and hydrogen. And so this will be our tiebreaker. So this will be number 2. This will be number 3. So we're going to go 1, 2, 3. So that's counterclockwise, which would be S. We reverse it. So it's going to be 2R. And remember, we reverse it because the lowest priority group is coming out in front of us. All right. Did anybody assign the stereochemistry of the other one? I'll just ask you guys before I do it. You got 2R, 3. Anybody? All right, well, let's see if we can figure it out here. Oh, somebody put something down. Okay, let's figure it out here. So this is going to be our lowest priority group. This will be number 1. This carbon is attached to oxygen, carbon, hydrogen. And this carbon is attached to carbon, hydrogen, hydrogen. So this one's the winner. So 1, 2, 3. Or sorry, 1, 2. Oops, 1, 2, 3. There we go. That's a little bit better. So we're going like this, which is going to be clockwise. So that's R, and the lowest priority group is going behind the page, right? So it's going to be 2R, 3R is what the stereochemistry would be for both of those stereocenters. So both of them are R. All right, does that make sense to everybody? I'll leave those notes up maybe, just so you can pause the video if you want to take a gander at them, right? So this is our lowest, where's my lowest priority. Okay, now the good thing is that now that we've named it as an oxirane, the stereochemistry isn't going to change. So the stereochemistry on the carbon on the stereocenter on the right is going to be R, and the one on the left is R. So we've got that figured out. So now all we have to do is name the compound as an epoxy compound. And so we got to find the longest carbon chain that contains the epoxide group. And so we're going to number it. How are we going to number it? We're going to go like this. We're going to say 1, 2, 3, 4, 5, 6, 7. So it would be 3, 4 epoxy heptane. So I'll scribble that down here. 3, 4 epoxy heptane. And then you have a stereocenter at carbon 3 and 4. They're both R. Okay, that's never going to change. It's just the numbering changes. So 3 is R and 4 is R. And there you go. Hot dog, we have a wiener. Okay, we did both of those. Let's try the next one. So we have an isopropyl group on one side and we have a methyl group on the other side. Well, let's give it the old college try here. We'll start out by naming it as an oxirane. So we have an isopropyl on one side and a methyl on the other. So isopropyl is going to win over methyl. And so we have group 1, 2, and 3. So we'd call it 2-isopropyl, 3-methyloxirane. So let me scribble that down. 2-isopropyl, 3-methyloxirane. Okay, so let's see if we can figure out the stereochemistry at carbon number 2. We'll start with that one. So with the one carbon number 2, so let's see here. Let me just put it, maybe I'll highlight this in yellow, something like that. Okay, so our highest priority group is going to be the oxygen. Our lowest priority group is going to be the hydrogen, which is in back. This carbon is attached to oxygen, carbon, hydrogen. This carbon is, well, this is our lowest. This carbon is attached to carbon, carbon, hydrogen, and so our tiebreaker is here. So this is number 2. This is number 3. So we go from 1 to 2 to 3. So we're going counterclockwise, and so it's 2s. So we'll scribble that down, 2s. And then for the 3 stereocenter, I'm just going to erase all this spinach. Zoink, like that. Okay, so now we're working on this stereocenter that I have highlighted in yellow. My lowest priority group is going to be going in back. So that's going to be 4. This is number 1. This is number 2. And this is number 3. So we go from 1 to 2 to 3. And so that's going clockwise. The lowest priority group is going behind us. And so that is going to be 2s3r. So there you go. And again, the stereochemistry is not going to change, okay? The only thing that might change is the numbering of the stereocenters, but the stereochemistry at the one on the right-hand side. So maybe I'll label it like this. This one is S, and this one is R. There's nothing we can do about that. All right, so now let's name it, excuse me, as an epoxy compound. We find the longest carbon chain, and we want to give the epoxy group the lowest possible number. So 1, 2, 3, 4, 5. So we have a 2,3 epoxy pentane, 2,3 epoxy pentane. And then our two stereocenters are 2R, and 3S. And there we have it. All right, give me a thumbs up, even if you just follow me on the rationale of those. Are there any questions about those assignments, the stereocenter assignments or anything? Because those can be tricky. If it, like I said, if it was easy, anybody could do it, right? You guys, I'd like to try a couple more synthesis problems with you. There was a couple that I thought were kind of neat. So, and I know you probably won't find them that neat, but anyhow, I thought they were kind of cool. So this is one I took from, I think it's an older version of the textbook. I'm not sure if it's in this version or not. So maybe somebody's seen this one, maybe somebody hasn't. But you start it with 1 pentene, and then you try to make a compound that's got a sulfide in it. So it's got a methyl sulfide, and then it's got an alcohol in it, in the same compound. All right? So a methyl sulfide and an alcohol in the same compound. And if you remember where we started out today, it said when you have two functional groups next to each other, then you want to think about starting with an alkene. So there's nothing really new there. But then it said, well, if one of them is an alcohol, you want to convert this into an epoxide. So you would start by converting this into the epoxide, like this. Maybe I can make that bond better. So you'd use MCPBA, like that. So that would give you the epoxide. And then if you want to create a bond, a sulfide. So what is our nucleophile going to be in this case? Well, we want to add S, right? We want to add a sulfur with a methyl group. So we're going to want to use a thiolate or a mercaptide, if you remember me talking about those last class. So where would you get that? Well, you would get that from sodium mercaptide or sodium methylthiolate, which is this here. And if you want to replace the Me with a CH3, like that means the exact same thing, right? So now this is a nucleophilic opening. So it's going to attack the least hindered carbon like this. We're going to pop the ring open, and that will give us something that looks like this. So now we've made the sulfide, and we have the oxide here. And now all we need to do is protonate it. You could use water or aqueous acid. I'd accept either one. It's totally fine with me. All right, so that's a ring opening, a nucleophilic ring opening. And there was another one that I thought was really cool.
Hey, Mr. Dion.
Yo.
Could you explain why, or if you could, or why you wouldn't use Br2 and H2O and then a Grignard?
So bromine and water, followed by a Grignard. Okay, so something like this. Is that what you're saying?
Yeah.
Okay, so the reason why you couldn't do something like that is there's no way. Well, first of all, you're not adding any carbons except for the methyl group, right? Which has to be attached to a sulfur. So if we had, 1 pentene like this, and if we treated this with bromine and water to make a halohydrin, right, what would that give us? That would give us something that looks like this, okay? So we would form the bromonium, and then we would crack that open like this. But then you wouldn't make a Grignard with this because Grignards are not compatible with alcohols. So remember, you can't have a Grignard in an alcohol in the same molecule without doing protection.
So that would just be too many steps?
Yeah, that'd be way too many steps. Yeah, because then you'd have to do a protection, then you'd make a Grignard, then you treat it with methylthiolate, then you could do a deprotection. So this is much, much shorter route. Does that make sense?
Yep, it does. Thank you.
Yeah, it's kind of a roundabout way. I give you, You know, I give you some serious points for effort on that one, though, Tiana.
Yeah.
I didn't even think about that. So yeah, kudos. I give you kudos on that one. Now, let me see. That's a great question. And by the way, anytime anybody has a question, don't be afraid to interrupt. But Tiana, when you said that, I thought it was my daughter behind me or something. Oh, I know which one I wanted to look at. Is this one here? I wanted to go over an acid catalyzed ring opening problem with you. I thought this one was pretty neat. It's very short, but this one here. So check this out. I'll just kind of demonstrate it for you maybe. If you have something like cyclohexanol, and the book says, okay, well, if you take this, how could you make something that looks like this, where you have an ether here, 2 carbons, then an alcohol, and have 2 methyl groups here, okay? And you might be thinking, whoa, that's, that's pretty heavy, doing something like that. Well, hold on, and I'll show you what it means, or what I mean by that. So what you'd want to do in this case, okay, is that if you're thinking about a retrosynthesis, remember I showed you the thing earlier that I said is not reality, but if you kind of make a disconnection like this, you could say, okay, well, in terms of retrosynthesis, I need to start out with a 3-membered ring, right, that looks like this. But the problem with this, compared to everything else that we've looked at today, is that you need to somehow get the nucleophile, right? The nucleophile has to attack here. It has to attack the most hindered carbon, which happens to be a tertiary carbon. And you can't just do that with a regular nucleophilic ring opening. If you want to attack a tertiary carbon, what do you have to use? What's your catalyst have to be? Anybody? And it's not a trick. Could anybody tell me what the catalyst is? Yeah, exactly. Thanks, Tiana. Exactly. It's acid. That's it. Thanks, Sydney. Perfect. Nothing more than that. So in order to get this to work, it's literally a one-step answer. Okay. All they're looking for is this: a catalytic amount of acid. So you can just write H3O plus and put in the electrophile like that. And that's going to give you the final product. Okay. That's the whole answer. Now, I think that at this level, you should understand the mechanism and be able to draw the mechanism of this reaction. So what's going to happen here is that in the first step, that epoxide or that oxirane is going to get protonated by the acid. So just bear with me here, and I'll kind of scribble my way through the mechanism here. So now that you've protonated, okay, the epoxide, you've created a much more powerful electrophile than it was at first, right? This is a weak electrophile. This is a very strong or powerful electrophile, I should say. It is ready and primed for a nucleophilic attack. And so now a weak nucleophile, like an alcohol, like cyclohexanol, an alcohol is a nucleophile, but it's a weak nucleophile. And remember, this is a tertiary carbon. This one is sorry, that's a primary carbon. What am I smoking here? That's a primary carbon. So remember, based on the electronic effect, the nucleophile is going to attack the more hindered carbon here because the positive charge is going to pass through that tertiary substituted carbon to make the most stable carbocation or partial carbocation, whatever you want to call it. So then after this step, what do you end up with? Let's take a look. So you end up with your oxygen. So you got 2 carbons. So if I count carbons 1 and 2, so this is 1 and 2, on carbon 1, you have a geminal dimethyl. On carbon 2, you've got the alcohol group, but notice that on the oxygen from the 3-membered ring, you still have the proton here, right, with the positive charge. So what's the last step going to be is that water, which is the conjugate base of hydronium, is going to come in as a base, and it's going to attack that proton and give you the desired product. Okay, I'll just write the word product, plus you're going to regenerate your acid catalyst. So that's an acid catalyzed ring opening. So let's scribble that up here. Acid catalyzed ring opening. All right. And I'm obliged to ask you a couple of questions about those along the way. So don't lose sight of the acid catalyzed ring opening. And the reason why this one caught my eye, this problem where it said make this specific compound that I'm putting in the blue box, is because I saw another question where I said, okay, we'll start with the same starting material. So start out with cyclohexanol. And instead of making that compound, why don't you make this compound? So it's an isomer, so you have 1, 2 carbons, then your alcohol, but all you do is put the 2 methyl groups on the other carbon. So see if I can squeeze these both on the same part of the screen. Look, you move the 2 methyl groups from here over to here is all we're doing. That's all we're doing. So how would you do it in that case? Well, in that case, if you do my kind of fake retrosynthesis method, if you break, if you make a bond here and you break this bond, you could say in terms of retrosynthesis, I would need, hey, look at that. It's the same old electrophile as before, but now I'm just going to use a nucleophilic ring opening, right? I'm just going to make a nucleophile out of my alcohol. Now, I don't need to use any kind of Grignard chemistry. I just want to convert it into the oxide. Could anybody tell me their favorite reagent to go from the alcohol to the oxide? I'll take whatever you got, what your favorite is. Any fan favorites out there? Could you use sodium hydride maybe? Right, well, why don't we try that? So sodium hydride, right? That's a strong base, okay? So that would give us the oxide. And now all we have to do is treat it with our 2,2-dimethyloxyrene like this. And this is going to behave as a nucleophile. It's going to attack like this. We end up making the precursor to the final compound. Oops. We have the negative charge out here. And then all we have to do is treat that with water or acid. Either one is fine. And that's going to give us the desired product. Anyhow, I thought it was a pretty cool, comparison of nucleophilic ring opening and acid catalyzed ring opening. And we'll cover it for chapter 13.